Okay, so today we're going to take a look at section 5.5. It's titled Solving Polynomial Equations. Solving polynomial equations. We'll do some solving and some factoring in this section. I want to start off with a factor problem that we should be familiar with, and then we'll introduce some new factorings. If we have x to the fourth minus 16. So this is not a quadratic, it is a fourth degree polynomial, it's quartic. But we can treat it and factor it like we did with quadratics. So when we dealt with quadratics, we talked about difference of two squares. We can think of this in the same way. This is the square, x to the fourth is the square of, we should know from the beginning section, we work backwards, it's the same as x squared squared. 16 is the square of 4. So I can think of it that way, and then I can factor it according to difference of two squares. So it'll be the x squared plus 4 and the x squared minus 4. Can we factor any further? Does x squared plus 4 factor any further? It does not. We can factor a difference of two squares, but not a sum of two squares. Difference of two squares factors, sum of two squares does not. So x squared plus 4 doesn't change, but x squared minus 4 can go to x plus 2, x minus 2. So there's some questions about why couldn't we factor x squared plus 4? Well, remember, I think there were some suggestions that maybe it's x plus 2 and x plus 2. But if you think about multiplying x plus 2 times x plus 2, you would get, yes, your x squared, but then you get a 2x, and then you get another 2x, which don't cancel out, and then you're positive 4. So in total, that's x squared plus 4x plus 4. That is not what we have. You also can't have a plus or a minus, or the last term is a negative. It would be a negative instead of a positive. So that is not factorable. Oops. Okay. Now let's consider a couple new factoring patterns. We had a difference of two squares. We knew that one already. We have kind of a lag here. There we go. So I should use, I suppose, a squared minus b squared. We knew before that factored a plus b, a minus b. That one's not new. But a difference of cubes and a sum of cubes, those are both new. Both of these factoring patterns, unfortunately, are a little more complicated than the difference of squares. Fortunately, though, they're very similar to each other. So you do have to know them, you do have to memorize them, but at least they're both very similar. The difference of cubes goes to this. You first have a binomial of a minus b. But then we have a trinomial of a squared plus ab plus b squared. And we'll try some of these in a little bit, but we need to know that factoring pattern first. And a sum of cubes is almost the same thing as that one, except we have to switch two of the signs. The binomial, instead of a minus b, is a plus b. And then the trinomial, the middle term, its sign will switch. So it'll be a squared minus ab plus b squared. So notice they're very similar. There are two sign changes from one to the other. And so now we'll go ahead and apply that. So let's just jump down here. We'll start our second factoring problem right here. Let's try a to the sixth plus b to the sixth. Now, I don't have them written as things with an exponent of 3, but I also didn't have that first problem we did over here written with exponents of 2. I had to kind of rewrite it or rethink it. So similarly here, if I want to think of these as perfect cubes, a to the sixth is the cube of, I might even switch colors here. A to the second. And b to the sixth is the cube of b to the second. So I will use, it is a sum, so I'm going to use the bottom factoring pattern. Everywhere there's an a, I will put in a squared. Because I was cubing a squared. Everywhere there's a b, I'll put in b squared. So the first binomial is a squared plus b squared. Then for the trinomial, I have to square my a. So I square a squared. I get a to the fourth minus, it says a times b, so a squared times b squared is a squared b squared. Plus b squared squared, that's b to the fourth. There's my answer. If I change one sign in this problem, let's try it. A to the sixth minus b to the sixth. It's a difference of cubes. We still get a squared cubed, but now it's minus b squared cubed. So I can use the other factoring pattern since it's subtraction. So this one up here, same thing except two different signs. A squared minus b squared. A to the fourth plus a squared b squared plus b to the fourth. And these instructions, I only wrote the word factor. I didn't write a big deal of instructions, but we will have to factor completely, meaning if you can factor further, you need to. And if you look at the binomial, it is a difference of two squares, so it factors further. So I'm not actually done. A squared minus b squared factors to a plus b, a minus b. The trinomial will not be factorable, though. So now there's our answer. The top one could not be factored because it was a sum of cubes. Question number 2. This one, or sum of squares, sorry. This one was a difference of squares, so that first binomial could factor further. Let's take a look at another factoring problem, not with the sum or difference of cubes, but something unique.
What are you doing?
Okay, so we have another factoring problem. Am I able to combine any like terms here? I do not have any like terms. I have an x to the 5th, an x to the 4th, an x to the 3rd, an x squared y cubed, an xy cubed, and a y cubed. They are all unique in their variable parts, so I cannot combine any like terms. But it is factorable. So this particular problem has 6 terms. And you will see some of these in this section. And we can factor it by grouping, possibly. Not every problem, but sometimes we can factor by grouping. We've done grouping before. When we have a 6-term polynomial, we'll probably be able to break it in half. Think of, and we could potentially have to rearrange the terms. I don't think we will have to in our textbook, but group it 3 and 3. The first 3 terms, do we see anything I can factor out of the first 3? And they all have an x to the 3rd even. I can pull out x to the 3rd from each of the first 3 terms. The first term had x to the 5th, so now I have x squared remaining. The second term, so plus, the 4 is still there. I took away 3 of the x's, so there's still 1 x remaining. And then from that third term, I still have the plus 4. I took away all 3 of the x's, so that's the end. Look now at the second grouping. Hold on. What do you notice in the second grouping? We can pull out y cubed. It is positive. I'm going to put a plus there. It is important later to remember that's positive. I cannot pull it out an x from everything. No. I can pull out a y cubed from the first one, leaving me with x squared. The second one I'm left with plus 4x. And the last term I'm left with just plus 4. Look at the 2 sets of parentheses. Are they the same thing? Yes. If they weren't, we didn't get anywhere. It wasn't necessarily factorable. This one, they are the same, so that is one of the factors. And then what's left? X cubed plus y cubed. So we've factored. Are we done factoring? Look at the trinomial, x squared plus 4x plus 4. Is that factorable? X plus 2 times x plus 2. Or I could write it as x plus 2 squared. And then what about x cubed plus y cubed? Is that factorable? Yes, if I scroll back up, that's my sum of cubes way up here, the bottom one there. So I can factor it according to that factoring pattern. So it goes to x plus y times x squared minus xy plus y squared. And now I'm done. They're not always going to be factorable, like where you can factor further, but sometimes they are, like this case. All right, let's take a look at this one. This one only has two terms. Is this one I see, we've got an x cubed, we got a y cubed, we are adding. Is this a sum of two cubes? This is not a sum of two cubes.
Thank you.
This is not a sum of two cubes. I do see a sum and I do see some cubes. But look at the coefficients. 2 and 5. Can you factor 2 and 5 out of both of them? No. There's nothing I can pull out of both of them. Is 2 a perfect cube? No. Is 5 a perfect cube? No. There is nothing I can do on this problem. It actually doesn't factor any further. It doesn't factor down at all. When we've had numbers, not polynomials, but when you have numbers that can't be broken down, what do you call those numbers? Like 5, like 3, like 7, 11, 13. Those numbers are prime. Polynomials can also be prime. We would call that prime because it could not factor. Okay, so what are some variations of this? What's something like this that might work? Well, if I had this and I could factor a 2 out of both, I'd have to do that first. And then what's left would have factored further. That's something I could deal with. If we had this, there's nothing I can factor out of both of those, but 8 is a perfect cube and so is 125. So I could have thought of that as well. That's 2x cubed. And then we have 5y cubed. And then I could factor that. I plug 2x wherever there's an a, and I plug 5y in wherever there's a b. So let's go ahead and finish that problem. You would have 2x plus 5y as your binomial. Your trinomial is the one that's a little trickier. You'd first take the 2x and you'd square it, which gives you 4x squared. Then it's a minus sign. And then you multiply the 2x and the 5y, that's 10xy. And then you have plus, and then you have to square the 5y, that's 25y squared. And so that would have been your answer. And the one up above, I don't want to confuse you by leaving the one up above it as is, it did factor. So if you're looking back at your notes later and you're wondering why we didn't finish that problem, here's what it would have been. So those are some things that do work. But example number 5 did not actually work because I couldn't pull something out of them, and 2 and 5 were not perfect cubes. The last thing that we need to do is come full circle now. The title of this section says solving polynomial equations. None of those were solving problems, but we can do some solving by factoring. So let's give that extension now. Since I'm moving into a different type of problem, I'm going to start over my number. I'm just going to call this number 1. Before I start this problem, what degree is this? It's a degree of 4. How many answers are we expecting? I would expect 4. Some could be imaginary. So it might not be 4 real, but I should find 4 answers. I heard someone answer 3. That would be like turning points. But if we're looking for solutions or zeros, there should be 4. Okay, we can factor this. It looks like a quadratic. Oh, my pen is. We can still do math, but give me a second. I have another pen, so give me a moment. All right, so this pen is not quite as easy to work with, so I'm going to zoom in a little bit. Oh, maybe it's the computer. It's not good. Oh, there we go. Okay, we're back in luck. Because of the x to the 4th, I have to have an x squared and an x squared. I do want to highlight something that must be true in order for that to work. The degree needed to be even, and then the middle degree needs to be half of whatever the first one was. And then it better just be 3 terms, and the last term is a constant. So if your first degree is even, your second one is half of that degree, and your third term is a constant, we can still factor it like quadratics last unit. But now I have an x squared and an x squared. 2 numbers that multiply to 48 add to negative 19. Three and 16, negative 3, negative 16. So we have it factored now like last unit. You would then set each factor equal to 0. So we know x squared minus 3 is equal to 0, and we know x squared minus 16 is equal to 0. And then from there, we need to square root. All right, sorry, solve both of those. I'm gonna go ahead and add the 3 over on that problem, add the 16 over on the other. And now I can square root. Remember, when you square root, you need plus or minus. That's where the other solutions are going to come from. So plus or minus the square root of 3 and plus or minus 4. Notice we got 4 answers. Positive square root of 3, negative square root of 3, positive 4, negative 4. Those are the 4 answers. I was expecting 4 and I got 4. Let's do one more solving problem. X cubed minus 64 equals 0. I could solve that by factoring, yeah? It's the fun factoring one, right? Or the fun, yeah, factoring problem. 64 is the cube of what? 4. Get x minus 4. Then it's x squared plus x times 4, that would be 4x, plus 4 squared, that's 16. So we factored it. And then set each one of those equal to 0. That one will actually, I would say this problem is easier to use a cube root instead of factoring, but we haven't talked about cube roots yet, so we're just going to go with what we've talked about so far. We'll learn about that later. So we get 4 as an answer to that one. Over here, is that one factorable? I don't think it's factorable. So how would I solve that? Well, you can use complete the square or you can use quadratic formula. I would use complete the square. I like it better. And Seems like people tend to be better at completing the square than quadratic formula. So I'd subtract that 16 over. What number goes in the blank? 4. You have to cut the 4 in half, which is 2, and square it. So 4, we add 4 to both sides. So we x plus 2 squared is equal to negative 12. What do you notice about what our answer is going to be? It's going to be imaginary, which is why it wasn't factorable. Not that that's the only reason, but x plus 2 equals plus or minus, and now we'll have the square root of negative 12. But we can simplify the square root of negative 12. We can think the negative 1 and the 12 can be separated. But the square root of 12 breaks down to square root of 4 and square root of 3. Square root of 4 equals 2. Square root of negative 1 equals I. Square root of 3 doesn't break down. So we have plus or minus 2i square roots of 3. And then to finish the problem, subtract. So negative 2 plus or minus 2i square root of 3. So one of our answers was 4, one was negative 2 plus 2i squared root of 3, and one was negative 2 minus 2i squared root of 3. We expected 3 answers. Did we get 3 answers? We did. If we would have graphed it, how many zeros would we have seen on the graph? We only would have seen 1. We would have seen the 4. The other 2 are imaginary, so they wouldn't show up on the graph. Our graph probably looks something like that. Maybe the loop is up above, but it only touches the x-axis once. We know that. All right, that is good enough for notes for today.